So, good morning, everyone. So I'm Renato. I was a PhD and a postdoc here for quite some time, and today I'm going to talk to you about detecting climate drivers of malaria using causality criteria. So we had some thoughts about it, a little bit about it yesterday, so I'm going to go over some things again. I hope you're not bored by it, but I don't know, maybe, yeah, it's nice to see something again, even if you understood the first time, then you are sure that you got it, right? So, well, so in a nutshell, what I'm going to present today, we want to investigate causal factors of malaria cases, okay? And we do that using a causality test based on attractor reconstruction, Coutinho's theorem, and so on. I'm going to talk a little bit about it. And the interesting thing is that not only we can do this thing in terms of, okay, this factor here is else or not. We can also look at it in more detail and detect, well, what is the interaction strength, what is the strength of the impact, what is the time lag, and this gives us some more biological insight than just answer causal or not, right? So, I'll begin by talking about how do you detect causality, okay? And then later I will apply it to malaria, right? So in a specific setting. So first, how do you, if you have only, so here I want to show you what do you do if you want to infer causality only looking at data, right? Because, well, of course you can use correlation, but everyone knows that, okay, correlation doesn't imply causation and so on, okay? What can you do instead? What you can do is, okay, you can build models and then fit the models to the data and then see if the model is a good fit or not and so on, right? But then, wouldn't it be nice if there was some way of doing that directly from the data, okay? So this is the idea, okay? Doing a kind of model-free causality test. So how do you do that? You have to somehow, so one idea is, okay, so let's try to think about dynamic health systems. So if you have a system like we saw, I think, Lais, right? Lais talked yesterday, and also Sergio told us something about it. If you have a dynamic health system, right, and you have several variables, okay, you have X, Y, Z, and so on and so on, okay, what Coutinho's theorem tells us is that if you measure only one of them, okay, with only one, you have a multidimensional system with many variables, you don't even know how many of them there are, okay, if you measure only one of them for long enough, right, if you go here and you plot, if you take X, for instance, and you plot X of t versus X of t minus tau versus X of t minus 2 tau versus, if you want more, X of t minus 3 tau and so on, right? So how many of these X's you need, I don't know, okay? But if you plot enough of this, you have something here, right, that can be mapped to the original attractor with all the variables you had in the full system. So this is the essence. This is a kind of a wonderful theorem. It's a really non-trivial, really surprising theorem, right? And here we have, you do know the Lorenz Attractor, right? So the butterfly and so on, right? So this is reconstruction from the X variable only, and this is from the Y variable only. And you see that they're pretty similar, right? So what I mean is, if you take a point here, okay, and there will be a corresponding point here, okay, and they will have, you can map one onto the other, okay. Well, I'm getting a bit ahead of myself here because what I just said is each one of those maps into the original dynamic system, okay. Okay, so how do you what can you do with that? So one thing you can do is you can try to do prediction, right? So if you have the attractor, you more or less, you don't have the equations, but you already know pretty much everything that happens in that attractor, okay? So for a long enough time, you should have all the information. So one thing you can do is prediction. So for instance, suppose that you have these points here are your attractor, okay? And you have the current point is this one, right? So how do you do prediction? Okay, you look at in the attractor the closest point, so I take these three here, and since they are these 3 points are in the past, you know what happened to them in the past. And then you project these 3 points in the future here, and then you take an average of these 3 points here to predict what happens in the next time step. So I don't know, is that clear? So I have another plot here that maybe it's a little bit easier. So what it means for to be close in the attractor, in the phase space, right? So suppose that I want to predict what happens after for that point here, right? So I take these 3 points, if I have a 3-dimensional phase space, right? I look at these 3 points and I look at the times in the time series in the previous times, what are the points that are similar to this point? So you see, you need 3 adjacent points that are similar to these 3 here, right? So I find these points here, okay? And then I look at each of those and see, well, what happens after in the next time step? This the item here, this the item here, this guy here, this guy here. So my prediction will be an average, a weighted average of those 4 values here to give you a prediction. And we see here that it kind of worked it, right? So, yeah? Is that clear now? Yeah, nice. So what can, well, we can of course measure how good this prediction is, right? So we can go over the whole time series and check, okay, what is the prediction? And comparing it to the actual observed value, and then this gives you you can correlate prediction versus observed values, and this gives you this correlation value, this prediction scale, okay? And now we want to use this this tool to infer causality. So the main idea is, well, I'm going to define causality in a specific way. So I'm going to say that 2 variables are causally linked if they are part of the same dynamical system in a way that they interact with each other, okay? So this is one way to define causality, okay? So if I have 2 variables, I have two time series, okay? Well, if I reconstruct the attractor from one of them and from the other of them, from those 2 separately, and they both map in the original attractor for the whole system, they map onto each other, right? Yeah, does that make sense? So if they map onto each other, then I say that they are causally linked. Good? Nice? Okay, so how do you do that? So how do you map one variable onto another, right? So what you do is, okay, here you have, so this is essentially the idea I just said, right? So you have the reconstructed attractor from X variable, from Y variable, and this is the original one, right? So if I have a region here that maps here and another that maps here, then this maps onto this, okay? So what you do is you try to predict one of the variables from the other. And if you have a good prediction, then you say that the mapping is good. So what you do is you look here. So remember, when we wanted to predict the next point in X from the X, the reconstructed attractor using the X variable, right? What did we do? We looked at for instance, you would take Y here, right? Or take X. We take the closest points here, right? And then see what happens for them for the next time. But now I want to use the Y points to predict X, okay? So what do? I take Y, the points I want to predict here. So here, usually we do it at the same time step. So I take Y of t and try to predict X of t, okay? So, question? Yeah?
There is a map between these 2 manifolds, or
Yeah, the map is essentially x of t corresponds to y of t, right? So you say that the points are mapped by having the same time index, the same date in the time series, right? So this is how we relate x points in x to points in y.
But you go from one manifold to the other through the original dynamical system?
I'm not sure I follow you.
I don't understand well how do you map mi to nx?
Yeah, so what I do is something like this. I have x of t for many points in t, and y of t in the same time points, okay? So x of t corresponds to y of t. So I use the time, yeah? So I take here the closest points, I take here y of t, and I want to predict x of t without using x of t, right? So I take the closest neighbors here to y of t, and I look at, now if I wanted to predict y of t, I use an average of these 3 points in y, but now I look at the corresponding values for x, and now I average those x values here to get a prediction. You see?
Okay. Yeah.
Yeah? Okay, so, and again, we can compare the predicted values with the actual values, take a correlation between those, and if you have a strong correlation, then you say that your prediction skill, your cross-mapping now, you're mapping from one attractor to the other, one manifold to the other, you say that you have a high cross-mapping prediction skill, okay? So this is going to be the main result for saying, oh, well, do these variables are causally linked? Yeah. So what do you need? How do we expect this to happen, right? So first thing, this correlation value should be higher than the correlation, the brute correlation between the time series, and also another criterion is as you increase the amount of data, the number of time points, the number of points that you use to build your attractor, right? What should happen? Well, if you sample more points in the attractor, right, in the manifold, you should increase your accuracy, right? So you should see that, so this is an example here, you should see that your prediction skill increases until it saturates as you increase the length of the time series you are using to construct the attractor. Then, hence the name that this is usually called, this is called convergent cross-mapping, CCM, okay? So this is originally proposed by Sugihara, so in this 2012 paper, this attractor construction goes back to the 80s, okay? But this idea of using it to detect causality, this is, I think this is the first paper that introduced the idea, okay? So this is recent-ish, right? So almost a decade, right? So, but this is true. So this here is actually two examples here. So this is an experiment with paramecium and looking at, well, does a predator causes the prey and vice versa? And the answer, well, yes, right? Well, this is kind of expected, right? So another example, a little more sophisticated, is using this sardine and anchovies and sea surface temperatures, and they show that actually sea surface temperature causes one of, like they seem unrelated, but actually the effect is really temperature, not interaction between the species, right? So this is interesting. So this is clear, yeah? Okay. So, well, the question then is, well, does it work, right? So does it work, right? So I showed you some examples that, of course, the ones that, yeah, they work, right? So, well, usually it's easy to find, if you test this with simulated data and so on, it's easy to find false negatives, okay? You don't see any sign, you don't see causality, but there is a deterministic part, and if you add a lot of noise, then the signals are blurred, and then you miss the sign, right? So it's easy to have false negatives, especially if you have a lot of noise. the better question is, well, okay, is it common to find false positives, right? So you calculate this stuff and so on, and you find causality. Are you sure of that? Well, the answer is almost always yes, right? Almost always. But there's one tricky case that is difficult, that is when you have a strong periodic forcing, okay? And then everything in your system becomes periodic, and it's like the seasonal pattern by itself is driving your system. Then you don't know anymore if what is driving your system is just seasonality in a general way, or if it's really like temperature or rainfall or what, right? So it's hard to distinguish between them, right? So here, now things become a lot more technical, right? So I'm not going to go into too much detail. But what we can do is, when you have systems like this, and this is, well, exactly the case we are interested in, right? So we are looking at, I'm trying to look at climatic drivers of malaria, right? So it's strongly seasonal, and well, so what we do is, well, we separate what is the seasonal pattern, the mean values along the seasons, from variation from this seasonal pattern, right? And then I try to build alternative time series for what I think are my causal variables. So I build a lot of artificial time series randomizing this variation around the seasonal patterns, right? So I do this, I do thousands of time series, and then I kind of build a distribution of holes of prediction skills, and then I look at my original data and I say, okay, with my original data I get a hole higher than, I don't know, if I take a 5% significance level, then higher than 95% of the, so this looks more like a statistical test, right? Okay? Okay. So now I want to talk to you about, well, malaria, right? So we are going to look at, not malaria in general, but we are going to look at malaria in Argentina, right? So it's not something that there's a lot of, right? So there's not too many cases and so on, right? Malaria in Argentina is essentially restricted to the northwestern part of Argentina. So this is near the triple frontier with Bolivia and Paraguay here, right? And we have, why is this interesting, right? Of course, there's always the point of, well, this is the data we had to work with at the beginning, right? So this is one reason, but there's also an interesting possibility here, is that this is the southernmost region that has malaria in the Americas, okay? So this is, as far as malaria goes, this is actually malaria vivax, right? And and there are very few cases. So I'm showing here, there's only, in 12 years, only 266 cases, okay? So we could say, okay, usually it's hard to say, okay, is prevalence or number of cases driven more strongly by climatic factors, or is there a strong epidemiological component? Okay, how many immune people I have, how many have resistance, and so on, right? But for this very low, I think this is for the city of Tartagal, right? So this is a city with 80,000 people, so this is a very low number of cases, and we can well, I think it's reasonable to assume that this is essentially driven by climate, right? So we should expect to have strong climatic signals, okay? So this is kind of, yeah, we expect this to work, okay? Okay, so this is malaria cases in this from 2000 until end of 2011, and they are typically from in the summer season from November to April, and then they don't appear in winter. And here we already have an issue here, right? So this is the red line here is a number of cases, right? So it's pretty common to have 0, right? Most weeks have a 0 there, right? And then that's problematic, right? Because, well, is it possible that, I don't know, in the middle, like even in the middle of I don't know, one of the biggest peaks here, you have some very low values here and so on, right? So this is probably related to measurement noise, okay? So it's hard to apply this method if you have a lot of zeros in your time series, okay? So you have to somehow smooth out the noise. So what we do is we do a kind of state space model just to estimate the number of cases, trying to take into account that there's noise in the measurements and so on. So we actually get this blue line here that has a kind of shadow here for the error, right? The credibility interval here, okay? And now we already have something interesting here because I told you that cases typically begin in November, right? But we do have data for mosquitoes in this region, right? So are close to this region. And the peak of mosquitoes is in October, right? So this is funny, right? So well, let's dive into it, right? So what do we do, right? So we take this number of cases, and here we have seasonal patterns we have minimum and maximum humidity and minimum and maximum temperature, weekly as well, right? So weekly values. And then we fit here this seasonal pattern here. Remember I told you about the surrogate, so these are the fitted seasonal patterns. And then of course there's something that it's not so nice here, is that we don't have reliable rainfall data. So this is something that would be very useful to test, but we just don't have the data, so cannot do anything about it, right? So, and we're going to test if these climate drivers are causing, potential climate drivers are causing the number of malaria cases, okay? So we do the stuff I told you about in the beginning of the lecture, okay? And now we have plots like this. So I have to explain this with a little more carefully, okay? So what do? Okay, we build the surrogates, and then we compare the surrogates, the whole of the original data with the whole of the surrogates, and then we test if this relationship is significant or not for time series of humidity, for time series of temperature, causing malaria cases, okay? And then we have an asterisk here can you see the asterisk, right? So this small dot and the asterisk, right? And we have an asterisk here if this is significant, okay? But now we can do something different, right? We can say, okay, we expect to find that climate takes, like, for instance, if you think in terms of temperature, right? So if you think in terms of, for instance, development of mosquitoes, okay? Well, how long until an increase, I don't know, in rainfall or temperature, how long does it take for this to cause an increase in the number of mosquitoes that then increases the contact rate between the number of cases, right? The contact rate between people via mosquitoes, and for this to reflect on number of cases. So this can be a long time, right? So if you have, like, depends on temperature, depends strongly on temperature, but you can have like a whole month for the whole development cycle of a mosquito, okay? So what do? We, instead of looking only at the raw time series, we also try to do this with lagged time series, right? So this plot here is actually that whole as a function of lag, right? So what do? We ask for, okay, if I take not the time series of humidity, but the time series of humidity lagged by 1 week, and then 2 weeks, and then 3 weeks, and 4 weeks, and so on. In each of these time series, I use the causal criterion I explained before, right? And then I see that for instance, for humidity, I don't have causality here for the series by itself. But if I look at the lag time series after, what is here? It's 13 weeks. Yeah, 13 weeks. Then around this 13 weeks lag time series here, I do have causality. You see? Is it clear what this plot means? Yeah, so I have the whole as a function of the lag between the time series I'm testing, right? And the asterisks are the significant relationships, okay? So, well, first, it's not surprising that there are a lot of asterisks here, right? Because if you didn't have any noise, so for instance, if you do this exercise here for the Lorenz equation with no lag and so on, with no noise, sorry, and do it for several lags, it is always significant, okay? Well, you lose a bit of those significant points here, mainly because of noise, right? So it's not surprising to have a lot of significant points here, okay? But what is interesting is you always get a peak here, right? So we have here peaks in minimum and maximum humidity at 13 weeks, and then for minimum and maximum temperature, we have for minimum temperature peaks, significant points here, close to between 0 to 5 weeks, and then for 22 weeks here, and here I think it's for 5 weeks for maximum temperature, okay? So you see, when we do that, we now have something else, right? We have some idea of how long is the delay between having an increase or a change in temperature or humidity, and how long does it take for it to have an impact on number of cases, right? So this is already interesting. And here we can distinguish two kinds of responses. Responses at low short time scales, right? And short time scales is usually related to what? To directly transmission, right? So, yeah. So factors affecting transmission, yeah?
So you can compare this lag time series with the number of occurrences.
Yeah. Yeah, exactly. Yeah, of course we always do negative lags, of course, because we don't want temperature to affect cases in the past, right? So yeah, so sure.
No, sorry, but you haven't lagged the original time series, the original instances.
The malaria cases is always as it is, and then we shift the climate time series. Okay?
So only these ones are the one who is shifted.
Yeah, because what is relevant is the relationship between the malaria cases and the climate drivers. Yeah? So we just shift the climatic ones. Yeah, but of course we would just shift the other one to the right, and then instead of, yeah, of course. Right? Clear? Yeah. Okay. So now we can think, okay, there are some short time lags and some long time lags, like here 13 and 22 weeks, right? So we expect the short ones should be related to infection, to parasite cycle, and how does temperature, so we see here that it's always temperature, right? So how does temperature affect transmission, right? So usually this happens because of extrinsic incubation period, EIP here, right? So this is the time that it takes for the plasmodium to develop inside the mosquito. So if you have low temperatures, this thing can take as much as 50 days, right? So does a mosquito live that long? No, right? So there's no time for the mosquito to bite again before the plasmodium develops, okay? Yeah? So you just don't have transmission anymore, right? Because the plasmodium takes so much time to develop that the mosquito is dead before that, right? So, yeah. And for long time delays, we think this is probably related to what? To development of mosquito population, okay? So if you have an increase in mosquito population, then of course you have an increase in the transmission, right? Okay. So there's something else that we can do now that is the following. So let me show you this. That is the following. So remember that when we try to do, when we do the mapping, right? What do? We take those points and the prediction comes from taking an average of points in the phase space, okay? So if we do something similar, but now using as your phase space your climatic drivers, okay? You can try to see, okay, in order to get a good prediction, we have some weights of this time series, okay? And these weights can give you information about, okay, if for this, I'm not sure if this is, yeah, this is a bit complicated. So we can look at the weights of each variable to see how it affects the number of cases. See, using when you do the prediction, you have to do those weights, and if you look at those weights again, you can say, okay, in this region here, for this point here, I'm using a stronger weight for temperature than humidity. In this other point here, I'm using a stronger weight for humidity than temperature. In this other point here, so for each point in your time series, you associate a weight in your weighted average, right? To each variable, to each causal variable. Is that clear? Yeah? So this is kind of an interaction strength, right? So what we can plot now is we can take those ones that were significant here. So this one, this here, and this guy here. And we can say, okay, what is the sign? Because this just tells you, okay, temperature lagged by maximum temperature lagged by 5 weeks is causing number of cases. But doesn't tell you in which direction this goes, okay? So if we want to analyze the strength of the sign and if it is positive or negative, we can look at this, okay? And then we see several things that are very interesting. So for instance, for minimum humidity, it's almost always positive, okay? So this is very noisy, okay? So this is very noisy, but it's almost always positive, and it's stronger for low humidity. So if you have a low humidity, increasing a bit humidity has a higher impact than when you are at high minimum humidity. Increasing humidity has only has a smaller effect per increase of humidity, right? And something similar, but in the opposite sense, happens here for maximum humidity. So if you have, this usually has a low impact, but for very high humidities, here around 90% and over, we see that increasing humidity is actually bad, right? Has a negative sign, right? Bad in the sense of, well, decreasing number of cases that is good, right? But, well, you see what I mean, right? So, right, so you have negative impact on malaria cases for high humidity, which is actually pretty surprising, right? So this is one fight we had with referees, right? Because, well, humidity is always new. This is kind of the given. But we saw that there are some lab experiments that do corroborate this. For very high humidities, you can have loss in terms of higher mortality also. Okay? For temperature, now it's more interesting. We have here for this is LAD 0, this is LAD 22. Both are for minimum temperature, and this is for LAD 5. Maximum temperature, right? And we see that minimum temperature doesn't have much effect. This is time lag 0, right? So this should be related to what? This should be related to extrinsic incubation period, right? So this only becomes strongly relevant when you have temperatures higher than 15 degrees here, you see? So, yeah, and then this becomes a strong factor, okay? For time lags of 22 weeks, right? So this is mostly development of mosquitoes, okay? Population growth. Then you always have a positive value, but for very high temperatures, it doesn't matter much anymore, right? So if you have some temperature, some minimum temperature high enough, then you don't need doesn't matter so much anymore, okay? And finally, this is also for short time lags, for time lags of 5 weeks. We see that maximum temperature always has a positive effect, but it also becomes more marked, but also more variable here when you have high temperatures, okay? Yeah? So you see, so we tested causality, so to conclude, right? So we tested causality, so we have seen that, well, at least this is a choice, right? But we see that CCM, the convergent cross mapping, can be used to unravel causal factors. And of course, I tell you model 3, I'm definitely not against models, right? I love models, okay? But it's interesting that you can do that, and you can even use that to also be able to better calibrate your models, okay? So now if I wanted to go for a model of this situation, I would probably think carefully about, well, do I need to take into account humidity? Yes, because it changes, it affects population dynamics and so on. So yeah, so it's easier to get, well, what should go into the model and so on, right? So this is one way to do it without doing the whole model first, okay? And also we can take this kind of information here. What are the time lags when these variables are more relevant? What is the interaction strength? And for which values of, so this is actually interaction strength as a function of your variables, okay? So it's not that temperature is always relevant. It's relevant when you are in a certain range of temperatures and so on, right? About malaria vivax in Tartagliao, okay? We see that this does happen as more or less expected, okay? So this is not very, very surprising. And we also find that we can relate this. This I didn't do this in a very detailed way. If you check the paper, then we have more references on development times and the times that extrinsic incubation period takes and so on to make this comparison more rigorous, right? More strict. But we are able to relate these causal factors to biological insights of the transmission cycle, okay? Well, I want to thank my collaborator, so Karina, and I want also to mention that this is actually came up from, Karina came here from an ICTP event, right? So this actually comes from a workshop pretty much like this one, right? So this is nice, right? So, and also Breno, was a postdoc here, and Paulo and Roberto is right here, right? So you don't need to, right? Well, thank you. Thank you. Questions?
I was wondering, I looked at the initial time series that you showed. It seemed like malaria was declining in that area, and I expect that in the final years, the cases may have been a lot of imported cases from other areas with different climate. I was wondering whether the strength of the relationship between the incidence and the climate changed with time.
Yeah, I don't know the answer for that. It's possible to have imported cases, but
I'm working on dengue in that region, and there is a lot of movement between Bolivia, south of Bolivia, and north of Argentina. There are a lot of temporary workers that come from Bolivia to Argentina and through all the years, so that may answer the question.
But the strength of interaction may change in time.
Yeah, I think
we don't have a plot of that,
but
but
explore.
yeah.
I just wonder whether it would be interesting to explore that, because you may be able to quantify through the strength of the interaction the amount of local transmission versus imported cases.
Yeah. Thank you. Yeah. the minimum and maximum in the whole week. So we have actually I think it's daily time series of temperatures, right? But we only have minimum and maximum, so it actually take I think it's the average maximum daily value. So this is exactly what is there, right? So
yeah. So have you tested for the mean and max, but not the mean and max average value of 1 week?
Yeah, I think we tested almost everything, right? So this is kind of a mess because at some point you have to decide what you're going to use, right? So we tested with like take the maximum, really the maximum, not the average of the maxima, and I think it gives you pretty similar results. Okay, I'm not sure if it's quantitatively like the values of whole change a bit and so on. It changes a little bit, but the general results remain the same. Okay, but of course you have to choose one because yeah. Yeah.
I forgot my question.
Did you compare what you obtained with proper variables of the mosquitoes?
Yeah, we don't have actually. I told you that we had some data for mosquitoes, but it's not in Tartagal. It's in a low city, so we can say something about the seasonal pattern because we know population dynamics of mosquitoes in a region that is very close, but we don't have number of mosquitoes in Tartagal in the period. So it's
not the same time study.
Yeah, yeah,
Much shorter.
yeah, exactly. It's not the whole time series either. So it's. Xanopheles, which one?
Pseudopunctipenis.
Yeah, exactly. Yeah, that's the one.
I remembered it. How much is left to explain after, so you can predict some of the variation?
Yeah. So the host, you're asking, can I get a good, sorry, but you're asking, can you get a good prediction? And the answer is, well, not so much, right? Because if you look at these plots here, right? So hold goes at most 2.5, so it's not a very high correlation, right? So it means that your correlation between predicted and observed values is only up to 0.5 or 0.6 at most. So it's, well, it's better.
But in any case, it's much better than just looking to the correlation between the time series.
Yeah.
Okay.
So it's an improvement over correlation over just doing a linear model, but it is still not very precise. So, well, depends on how glass, how full or how empty, right? So.
I wonder if that varies with time as well, because of this sort of concept of when you get down to low levels, it's not local transmission anymore, but it's more like random introductions from imported cases.
Yeah, but it's hard to do that for like, because you do need to, in order to do the whole analysis, you need at least a few years, at least some 5 or 6 years, otherwise you cannot do the analysis at all, right? And we have 12, so the best we could do is like, do it with half the data and then the second half, the best, right? So it could be possible, yeah, but it's kind of, you get a lot more noisy results because of that, less data.
More questions? Have you tried to calculate the dimension of the original dynamical system?
Well, I didn't comment about it, but actually all of this is done with some dimension, right? So each when you include, we use this whole to choose the embedding dimension. So we choose the embedding dimension that gives you the highest whole, okay? But then this gets pretty high, right? So sometimes you get 9 or 10, I think, right? So for embedding dimension.
We had a maximum allowed value of embedding of 10.
Yeah,
So
but it sometimes reaches the maximum, right? So yeah, yeah, it's never less than 5 or something like that, right? But yeah. So.
when I'm using the convergent force mapping, we're assuming that you have a finite dimensional map.
Yeah.
But you are using the time lags to compare it. So it appears that all your seasonal effects are appearing as a delay factor. So it's not a finite dimension anymore. So if you are putting everything in the same dynamical system, you are putting the seasonal effect as a time delay time. So in the original time series infection. So
Yeah, I think this would be a problem. I think this is a hard problem in general. I think here is not so much of a problem because actually malaria cases do not affect, or at least we hope that it does not affect climate, right? So,
we're not putting the same dimension, just using an external force.
Yeah.
Okay, so thank you, Renato. Next speaker is Rodrigo Carter from the University of São Paulo.